Swayam Prabha. Digital India. Educated India.
Good. So today we are switching gears. So we looked at LSH yesterday, and today I'm going to talk about Bloom filters, right? And so I think you have already had some exposure to Bloom filters already. No? Okay, fine. But anyway, so this is going back to your familiar stream mining setting. So that all of you have been exploring quite a bit now, right? So the idea here is that we are going to be filtering data streams. So we're going to assume that each element that comes in the stream is some kind of a tuple, and each tuple has a key, right? And I give you a set of keys or a list of keys, yes. Okay. So as the elements are coming in the stream, I should only pass those elements that are there in the set, yes. Okay. So obviously you can use some kind of a hash table, right? But what typically happens is that for many of these applications that we will look at, right, the set S is very large, right? The set S is very large, running into say perhaps like a million or a few million whitelisted email addresses or URLs, right? So I have a secure website. So when an access to the website comes in, I should permit it only if it comes from a whitelisted URL. Okay, and that, imagine that, right? So how many URLs you might want to store? Right? It could run into millions of URLs. Right now, if I'm going to say that somehow I'm going to build this hash table that will allow me to quickly retrieve the URL if it's there or not, right, might require a huge amount of memory. Right. So the obvious solution that we are going to go for is hash it into something much more smaller, hash aggressively, right, so that the memory requirement comes down significantly at the cost of, there has to be a trade off, right? What could be the trade off? Space. I said you are reducing space at the cost of something else. See, this should be popping up to the top of your minds after all the LSH things we looked at yesterday. Correctness, right? At the cost of correctness. So I might let through some things that are not supposed to be let through. Might. Okay. If I am willing to accept that, then I can set up something that's a lot more efficient in terms of memory footprint, right, lot more efficient in terms of lookup time, because you are going to use hashing anyway, right. So that gives you that efficiency, but there is one very small probability of things that are not on yes sneaking through. Okay. So that is basically what we are going to look at. So here is an example, like a billion good email addresses, right, and if an email comes from one of those, it is not spam, regardless of whether they are writing about Nigeria or not, it is not spam if it comes from that email address, right. And then there are these publish subscribe systems, right. These are the idea is that you publish a lot of content out in the world, right, but people are interested only in some fraction of the content, some subset of the content. So what the subscriber to your website will do is that they will set up the keywords, or they will set up the topics that they are interested in. So when you publish something, right, you pass it through that filter and show it to the user. So if it contains keywords that the user is interested in, then you show it to the user. If not, you don't show it to the user. The challenge here is that each user might not give you a billion keywords. Maybe a user gives you maybe at best 1,000 keywords or something they are interested in, but you might end up having a few million users. right? Instead of one filter trying to filter billion things, you might have a million filters trying to filter 1,000 things each. So, if you am going to run these million filters in parallel, I will still need a lot of memory. So, we have to do something cleverer about it, right. And more than the spam filtering application, spam is fine, this is also fine. If you have some small number of spam emails that find their way into your inbox, you are okay with it, right. Or if a small number of articles that are not of interest to you come to you, you are okay with it, right. So, what the Bloom filter will guarantee is that no good email will get filtered as spam, right, and no real news story that should be published to you will be missed out. So, we will assume there are no false negatives, there will be false positives, okay, that is basically what the Bloom filter does. So, the idea is actually fairly simple, right. So, given a set of keys that we want to filter, so you create a bit array B, right, of n bits, initially all zeros, right. So, then choose a hash function h that will hash into the range 0 to n minus 1, right, hash each member of S into one of the n buckets and set that bit to 1, whichever bucket it hashes to, set the bit to 1, right. Now, in the stream, as and when the elements come, you hash it into one of these buckets, and if that bit is 1, you let the element through. If the bit is 0, you filter the element, okay. Now, think about it. So, if there is the stream contains an element that is in S, because by definition when you initialize the bit array, you already hashed S into the bit array, right. So, you know for sure that if an element in your list S comes again, it will hash to a bit that is 1. So, no false negatives, every true element will go through, right. But then it is also possible your hash function is hashing elements not in S into a location that has a 1. So, in which case you have false positives, okay. How bad could the false positives be, okay. So, that is basically what it is, right. So, just illustrating it. So, if the item hashes into 1, then you output that, and if an item hashes into 0, you drop the item, right, because it is surely not in S, that much we know, right. If it hashes to 0, it can't be in S, because every bucket S hashes to, we have already set to 1, okay. So, how bad is it, right? Let us say that I have a billion email addresses, right, and I have a spare memory of 1 GB, right, which I can use for this bit bucket, right. So, that is about 8 billion bits, right. If the email address is in S, that is fine, no false negatives. So, now if you think about it, because I am hashing a billion email addresses into 8 billion buckets, right, roughly 1/8 of the buckets will have a 1, right, at most 1/8 of the buckets will have a 1, the rest will have zeros, right. And if my hash function is truly uniform, that would mean that about 1/8 of the addresses might actually go through of all the things that come, right, about 1/8 of them might go through, right. So, you can think of the false positives as being a false positive rate as being something like 1/8. So, 0.125 is my false positive rate. So, that means of all the things that are not in S, right, 12.5% of them might actually go through. Seems like a large number, right. See, it depends on how you are implementing it. See, Outlook might just be sending Gmail to spam out of spite, No, but it depends on how you are implementing it, right. So, if you have a whitelist, right, so almost all mail clients allow you to specify a whitelist, right. Remember, I do not know how it works in Outlook, trust the sender. You can click on trust the sender, right. So, if you say trust the sender, then it is a whitelist, right. So, one way of implementing whitelist is using a Bloom filter, right. But if your whitelist is really small, right, and it is implemented in your end, not on the server end, right, a Bloom filter might be an overkill. So, because you and I will probably create a whitelist of about 40-50 email IDs, right, and if it is running on your server end, right, I mean not your client end, right, it is running on your email client, you are filtering, you are implementing the whitelist. So, what does that mean? That the mail actually comes to your machine, your Outlook client, and there it is pushed into a spam folder, as opposed to being processed centrally in the cloud, and then you are getting only what is there in your inbox, and then when you click on spam you go get it from the cloud. Instead of that, if it gets locally processed, then you can just do a simple comparison lookup table, because you have only about 100 email addresses that are whitelisted, and I hope you are not getting millions of email addresses a day, no, right, emails a day, right. So, if you are, then you have to change something else. Okay.
Once I have come across it as scenarios, so I thought that I missed that mail as I received.
Oh no, it's painful. I should tell you, both Outlook and Gmail filters are not foolproof, right? And unfortunately, since both of them keep adapting their email filters all the time, you just keep getting new corner cases all the time, right? So, you have to periodically keep checking your spam folders, right? So, let us try and do a little bit more accurate analysis for the number of false positives. Right now, I just did kind of a hand wavy thing and said it is about 1/8, right? So, let us look at that, right. So, this analysis kind of is modeled as throwing darts, right, a simple way to think of it. Suppose I have n targets, right, this is kind of corresponding to our bins, right, and I am throwing m darts, okay, at these n targets, throwing them independently, right, and I am equally likely to hit any one of these targets, okay. So, what is the probability that a target gets at least one dart? Right. So, that is basically what we have to look at, right. So, the targets that do not get even one dot are the empty ones, right. So, the targets that get at least one dot are the ones that can potentially leak through spam IDs. So, we have to look at that, right. So, that we know, oops, okay, the animation is coming, it's a little out of order, but that is fine. So, the probability that some target X is not hit by a dot, right. So, 1 by n is a probability will hit the target, and 1 minus 1 by n is a probability it will not hit the target, right. Okay. And remember, we are throwing m dots, right. So, 1 by 1 minus n the whole power m is a probability that all the m dots do not hit the target, right, and 1 minus that is a probability that at least one dot hits the target, okay. So, that is basically what we have, and that is just a multiply and divide by n. So, why we do that? Oops, I pressed 2 again. So, that is 1 by e as n becomes large, right, 1 by n power n, right. So, now I can rewrite this as 1 minus e power minus m by n. So, that is a probability that the target gets at least one dot, right. So, let us look back at our example here, right. So, we had a billion addresses, I think, right, and 8 billion targets is what we had, and so the fraction of ones is going to be 0.1175. So, 1 by 8 was not too far off, right. Okay, good. So, can we do better? Can we kind of quote unquote amplify this? Just think about how we did this for LSH, right? So, we took one hash function, showed that it had some properties, and then combined many different hash functions and kind of amplified it so that we got better, right? So, what will be the trick to amplifying this? Use more than one hash function, right? So, we used one hash function, right, and for these numbers, right, so 1:8 ratio, then we get about 0.1175, right, is the fraction of false positives that you might get, right. Now, what I am going to do, this is the actual full Bloom filter, is to use k independent hash function. So, I am going to have, so S is the number of keys I am interested in, that set that I am interested in, and B is the number of buckets that I have for my hashing, right. I am going to use k independent hash functions, but because I want to make sure that our memory restrictions are there, right, are maintained, we will just going to use a single array. It is not like I am going to have k arrays of b bits each, right, k arrays of n bits each. So, I am going to use a single array of n bits. So, right, so set all the b's to 0. So, when you take an element in S, use each hash function, and whatever value that hashes to, you set that corresponding bin to 1, right. So, earlier I had hashed m times, right. So, I was hashing m times and setting it, now I am going to hash mk times, right, and then set those bits to 1, right. So, at a runtime, what do I do? When a stream element arrives, right, I am going to hash it using each one of those hash functions. I am going to do k hashes now, and only if the element hashes to a 1 under each one of those k hash functions, I will declare it as a valid element. It has to be under every one of those hash functions. Why? Because we know that if the element was there in S, we have already hashed with all the k functions and set it to 1. So, even if in one of those hashes it misses the 1, then it has to be a false positive, right, then we will kick it out, we will not accept it. So, that is basically the idea here, right. So, it has to happen for all k, otherwise we will discard the element k, right, make sense? Yeah, great. So, now again go back to throwing darts, right. Now, instead of throwing m darts that we did earlier, now we are throwing k times m darts, right. So, just the same analysis will work here. So, instead of m by n, e power minus m by n, we are going to have e power minus km by n, okay. But then there is a slight difference here, right. So, this is the fraction of ones, that does not change, this is the fraction of ones, but I am going to sample this fraction of ones k times, and I need to get a 1 every time, right. I am going to sample this bucket k times, I am going to get again 1 every time. So, this basically goes to the power of k. Okay. So, now let us look at this. So, I have this original numbers I had, m equal 1 billion, n equal 8 billion, and of course, k equal to 1 is what we saw already, it's 0.1175, and k equal to 2, big change, 0.0493. Great. So, what happens if I keep increasing k? K equal to 3, 4, 5, 6, 7, 8, 9, 10. Will you see this continuously decreasing? Okay. How many of you say the probability will keep decreasing if I keep increasing k? 1, 2, 3, 4, 5. You said yes, but you are no longer sure. 6. Huh? Up to a certain point. Okay, so why? Why only up to a certain point?
The difference will keep getting less and less.
Okay, you are just saying it will keep getting less and less, and it will just converge to some number. After that, it will stay the same. Okay. Okay, let me ask you this. How many of you say that after some point the probability will start increasing. 1, 2, 3, 4. Okay, why?
This is not necessary that if we increase the number of hash functions, it is not necessary that every hash function will map that particular element to one. After a particular threshold, I think the error probability will increase.
It will, but the explanation is not quite right. Anyone else? Very simple. As I keep increasing the number of hash functions, right? So the number of times I have to probe increases, right? That's the reason why we have the power k there and things get better. But what else increases? The number of dots I throw in the first phase increases. So as k becomes larger and larger, more of the bit buckets get filled with ones. Correct? Because I am throwing k times m, right? So more of the buckets will get a 1. And therefore, when I start randomly sampling, at some point I am likely to hit a 1 with a very high probability after a large enough k. So for example, simple thing, right? So once I reach k of 8, right? So I have 8 billion dots that I am throwing. I mean, I have only 1 million entries, but I am going to hash them 8 times. So literally I am like throwing 8 billion dots at 8 billion buckets. Right. At that point, the probability that I am going to start filling up the entire bucket, the bit array becomes large, right. So therefore, it does not work that well, right. So basically, what happens is you get a curve like this. That is a minimum at some point, right, and you can work out what that minimum should be, right. And in case that it turns out that it is n by m ln 2, and so for us it is about 5.54. You can see that somewhere around here, around 6 is where you get the small, the least value, right. So this is around 6. So the error at k equal to 6 is 0.0235. So the best you can do with Bloom filters with this kind of a setup, right. So if you want to improve this, what do you have to do? Fine. So best with this, right, 1 billion entries and 8 billion buckets is 0.235. So that is basically 2.35% of the entries will come in as false positives. Okay. So if I want to decrease that further, what should I do? Engineering question. Increase n. Right? If I want to decrease this further, I have to increase n. Remember the, right? So the more buckets I have, the more zeros I am going to have, right. So if you want, so these are all engineering stuff that you can do, right. So that's basically it. That's why I told you, right. Bloom filters, I don't think it will take the full time. So it's a summary. Bloom filters guarantee no false negatives, right, and use a small memory footprint compared to storing all the elements that you want to compare, right. Great for pre-processing. Before we move on to more expensive checks, right, if at all, it's very important that you don't allow any white blacklisted things to go through. What should you do then? Just take everything that goes through, make sure you eliminate false positives, right. Remember, we talked about it yesterday. False positives can be handled. It's the false negatives that are a problem, right. We don't have any false negatives, so that's good, but false positives you can handle with a second check, right. But another big advantage, and this is something that a lot of people do use, right. Bloom filters can be implemented in hardware, right, and there are many places where there are hardware implementations of these Bloom filters. So the advantage is you have already done everything, right. So you have this hash function and you have this bit bucket, right. So you implement all of these hash functions in parallel in hardware, right, and they will, each one of them will give an access to an element in the bit bucket, and then you basically get it through that element and then you AND everything. So if the AND gives you a 1, then you let the thing go through, right. It's very simple. It's basically like, maybe 3 gate delays or 2 gate delays or something. In hardware, it's extremely fast when you are implementing this. So that's one of the biggest advantage. And okay, here is this other question that I actually told you earlier, right. So you could either have one big B and have all the hash functions hashed to the same bucket, right, or same set of buckets, or you could have, for each hash function, you could just divide that large memory into k chunks, right, and you can give one set of buckets to each hash function, right, which is better. Because the slide tells you it's the same, but you have to convince yourself, right. So what we did here is that we threw k m dots at n bins, right, and what we are doing here is throwing m dots at n by k bins. So even though it looks like k small b's might be better, it turns out they are the same. So you can avoid the overhead of the bookkeeping, right, and then just use a single so that's basically what it is. One big B is simpler. Yeah. Cool.